Okay. And here we go. All right, so something called Le Chatelier's principle is the last big topic for this, and named after a scientist. And it is when we get to equilibrium. So we're talking about now something that has a system that has already achieved equilibrium, already achieved equilibrium. So Le Chatelier's principle is an idea of how a reaction, once again, I keep stressing it, is already at equilibrium. So we're now K applies, the products over reactants, coefficients become exponents, all of that applies. In the ice chart, we're at the equilibrium part. We're not at the initial or the change. We're at equilibrium already. All right, so we're at equilibrium. And then what happens is it gets perturbed away. The other way it's described is a stress is added. So something happens to this system at equilibrium that messes up one of the components. So now we're not at equilibrium anymore, because if we change the concentration of something, we increase it. Now it doesn't fit into the products over reactants, coefficients become exponents, law of mass action, or the equilibrium expression. All right, so Le Chatelier's principle states if a chemical system at equilibrium experiences a change, then the equilibrium shifts to counteract the imposed change and a new equilibrium is established. We want to look at this as an ice chart, right? I said we're at equilibrium, we're at this point. But then we do another change occurs. So now we're not at equilibrium anymore. So now with this change, you could look at it as being a new set of initial conditions. And then once again, a change has to occur so that we can reestablish equilibrium. By change, we're moving the system away from equilibrium such that Q is not equal to K. We understand the direction the system needs to move to reestablish equilibrium by thinking about what happens to Q when the stress or the change occurs. We will deal with three particular examples: adding or removing a reactant or product, changing the volume, or changing the pressure, or changing the volume, which results in a change in pressure, which only deals with gases, and then if you change the temperature. All right, so the beginning part. Le Chatelier's principle and changing the concentration of a reactant. Now it says pressures if we're talking about changing a gas pressure. All right, so if a reaction mixture is at equilibrium, and if you add some of the reactant, so we're adding more reactant, according to Le Chatelier's principle, the reaction will change in order to counteract that change. In other words, it's going to shift either left or right to undo the changes you made and reestablish that K value. Therefore, if reactants are added, it shifts to remove some of those reactants, and this can be accomplished by shifting towards the products. So if you add more reactants, it shifts away from that increase in reactants. The way that I always describe this is if you look at it as a seesaw, so where the arrows are the fulcrum of the seesaw, we've added more reactants. So that side of the seesaw got heavier, if you will. So how does it shift to counteract that increase of reactants? Well, it shifts to the right so that we can reestablish a nice balanced equilibrium. So we've added more reactants and it shifts to the right. The opposite would be true if you added more products. It's going to shift to the left. Now why? Well, remember, we're really talking about Q versus K. So products equal, or Q equals products over reactants. If we're adding more reactants, that means Q is less than K. Why is Q less than K? Well, we just added more reactants. We added more of the bottom number. So this thing had to shift in the other direction. We had to increase the products and decrease that reactant in order to reestablish our equilibrium. And they have some graphs showing it. So they show here, so we're at equilibrium. You can see the nice flat lines here. We're at equilibrium. The reaction is right here, where N2O4 is in equilibrium with 2NO2, and our concentrations are not changing until we get to this point right here. So at this time right here, you could see they added a bunch of NO2. So we've added product. What happens when you add products? Well, we've added some products. In order to reestablish equilibrium, we need to shift left. Well, if we look at this as Q versus K, we've added products. So Q is greater than K in this case, which means in order to reestablish equilibrium, we need more reactants. So it shifts left. How do we see that in the graph? Now, obviously, we have more NO2. So when we say NO2's concentration is going to decrease, we mean decrease from the increase that you added, not from where we were. So when we say that it's going to shift left, what that means is the concentration of NO2 is going to decrease, goes down, and the concentration of N2O4 goes up until, once again, we've reestablished equilibrium. Now, if we were to calculate K with those concentrations and calculate K with those concentrations, they're going to be the same. So an increase of reactants or products does not affect the K value, only whether it shifts. Same over here, but this time you can see they added a bunch of reactant this time. And so it shifts towards the product. You can see NO2 goes up, N2O4 goes down. All right, so adding reactants or taking them away, we didn't talk about removing them, that would give you the same effect. So we'll lead to a situation where either Q is less than K or Q is greater than K. And as I said, we understand those shifts. So we got that. And if you want to, you could memorize it rather than reasoning it. But like I said, I like to reason it products over reactants. Now recall, pure solids and liquids do not appear in the mass action expression. Therefore, if you add more of them, it does not affect the equilibrium at all. So no shift is what you're going to get. Now, solubility, I think, is a pretty good way to think about this. Think about, we have some water, and we throw in some NaCl. So we make salt water. Now, we just add a whole bunch. We're not measuring it. We're just adding a whole bunch. And so we're going to saturate the solution. So it's going to break into sodium ions and chlorine ions. But if we add a whole bunch extra, you're going to have a bunch of NaCl solid that settles to the bottom. So here's what we're talking about. It's at equilibrium right now. It's at equilibrium, and the reaction would be NaCl solid is in equilibrium with Na aqueous and Cl minus aqueous. All right, so there's the situation we have here. Not an unreasonable thing for you to be able to figure out. So if I do the Kc expression for this, it's the concentration of the sodium ions and the chloride ions, not the NaCl divided by, because it's a pure solid. So as we said, pure solids not included in the mass action expression. So now this is saying if you add more of them. So let's say we go back to our situation here and I add a bunch more NaCl. Now, no more can dissolve. It's saturated, it's at equilibrium. You can't have any more Na plus and Cl minus ions in that solution. So any NaCl I add is now going to settle to the bottom. Did it affect the concentration of Na plus or Cl minus? And the answer is no, it did not. So there was no shift in this equilibrium expression by adding more NaCl. All right, therefore, there must be a change in the concentration or pressure, if we're talking about gas, in the mass action expression in order to affect the equilibrium. Now, finally, that same solution we're talking about, it is possible to change the concentration of all the species at the same time by adding more solvent, so dump in more water, in other words, diluting it, or taking some of the solvent away by evaporating it. So now if we think about that situation here, so if I dump in more water, I've now increased the concentration overall. I've increased the volume overall, which is going to affect the concentrations. Now, how does it affect the concentrations? Well, molarity is moles divided by liters. We've just now increased the volume. So that decreases the molarity of those. So what's going to happen if we add more water is it's going to shift to the right this time. Why does it shift to the right? Because each of these concentrations effectively goes down. So if we could look at it as Le Chatelier's principle, you're decreasing the concentration of Na plus and Cl minus. by adding more water. And so it's going to shift to the right. Now this says it's going to always shift to the side with more species in solution. So more aqueous solution or substances, it will cause it to change. So we could have a change in Q. Now, when would we not have a change in Q? Well, if we had the moles of aqueous that were the same on both sides. All right, so the reaction will then shift towards the product side to reach equilibrium. If there are more species in a solution than reactants than products, then it will increase. And you're going to shift towards the reactant side then. All right, so you're always going to side with more aqueous species, more moles of aqueous substances. When you dilute a reaction at equilibrium, the reaction will shift in such a way to increase the total concentration, meaning moving towards the sides of the reaction with a greater number of species in solution. Think moles. If you remove the solvent, then it's the opposite. So you concentrate the solution instead of diluting it, and then the reaction will shift towards the side with fewer moles of aqueous. All right, what about if we're changing volume? So now this is often discussed in a movable cylinder. So we have maybe a syringe, you could have it, or a piston in a car, but you have a gas trapped in a container where you can change the volume. So changing the volume. You can also think of it as a balloon, you can change the volume. By changing the volume, you keep the constant pressure. So if we increase the volume of that gas, it keeps the pressure constant by expanding. All right, so changing the volume of a container with a reaction mixture is essentially only possible for a reaction involving gases. So this will not affect solids, it won't affect liquids, it won't affect aqueous. It only affects gases. First, let's look at Le Chatelier's principle. So if we mechanically decrease the volume, so I'm taking that piston and I'm decreasing the volume of the container that has the gas, the pressure inside the container increases, goes up. Volume goes down, constant temperature, pressure goes up. Since the change we made was to increase the pressure of the reaction will shift in such a way to counteract that increase in pressure by decreasing the pressure. How can it decrease the pressure? It can be achieved by moving to the side with fewer gas moles or molecules. So moles or molecules, look at the coefficients. Two key ideas. First, this is only in effect for reactions, again, that are gases. So solids, liquids, aqueous, no effect when you change the volume of the pressure. Now we're talking about changing the volume of the container, not the volume of liquid like we did in that last one. So different. So second, the volume only affects reactions that have different moles of gas on the reactant than the product side. Now, why is this? Well, again, think Q versus K. It's easier to see if we look at an example reaction. So look at this reaction we have right here. Pretty simple. We have two NO2 gas molecules in equilibrium with one N2O4 gas molecule. So Q is equal to the pressure of N2O4 over the pressure of NO2 squared. So we've got to square that one, remember, 2 in front. So if you increase the pressure by decreasing the volume, so we're increasing the pressure by decreasing the volume, we're squeezing that syringe. The partial pressures will increase. So the partial pressures of each gas are going to increase. Why? Well, the pressure goes down. The volume goes down, the pressure goes up. The pressure goes up for all of the gases. On the reactant side, we have 2 moles of gas. The pressure of the reaction side then are the pressures are squared, right? P over P squared. This means that the effect will be larger for the reactants than the products. Dividing by a bigger number makes Q smaller, and you'll find that after increasing the pressure, then Q is less than K. So if Q is less than K, you shift to the side opposite, so the product side in this case, and that would be the side with, again, the fewer moles of gas or the fewer molecules of gas. Similarly, if we do the opposite, so if we increase the volume, so if I increase the volume of that syringe, the pressure inside now decreases. So now in order to reestablish equilibrium, it needs more pressure, so it shifts to the side with a greater number of moles of gas. If the reaction has the same number of moles of gas on both sides, then a change in pressure or volume has no effect. Now, another way that they can change the pressure or the volume is by adding another gas that is not involved in the reaction. Oftentimes they'll add helium, an inert gas like that. They'll also use things like nitrogen. If the nitrogen is not part of the reaction, because it'll be there, kind of like air, right? It's in the air. We light a candle, we don't think about the nitrogen. It's just there. It's an inert gas for that particular reaction. Okay, so finally, sometimes the volume is increased. So now that's really, I think, how you can remember this one. So now we're increasing the volume. How? Well, think about our syringe again. We have this nice, happy syringe, and let's say we have A and B in there. Doesn't matter what the gases are. We have A, B. A is in equilibrium with, let's say, 2A. That way we have not a 1-to-1. All right, so now we're going to increase the volume of this, but not by stretching it or decreasing the pressure. Instead, we're going to pump in some helium, let's say. So we put in some helium. Now, what's going to happen to this? Well, if it is maintained at a constant pressure, which a syringe is, right, the pressure inside of there isn't going to decrease because I add some helium. What happens instead is it just makes a little space for the helium by effectively increasing the volume. Now, when you increase the volume, how does that affect our mixture? All right, so in this case, the total pressure is going to remain constant, right? Constant pressure because it's pushing against the atmosphere. But the partial pressure of the reactants in the products are going to decrease. Why? Well, because we've increased the volume. So if we increase the volume, it decreases the pressure. This is because the total pressure now includes the pressure of the helium in my example. This has the effect of diluting the mixture and is identical to simply mechanically increasing the volume. So in my example of 2A and B, if we add helium, volume goes up, the partial pressure of each gas goes down, and so it goes to the side with more moles. Pressure goes down, more moles. Pressure goes up, less moles. There's another way you could do this, though, and you can increase the pressure not by changing the volume this time. So this one's different. This is not a syringe, but this would be a rigid container. That's how they describe it. So maybe a 1-liter container, maybe a box that cannot change, a metal box, or a Erlenmeyer flask with a stopper in it. So once again, can't change volume. So no expanding and contracting this time. So now if I have my A, and B in there, and I pump some nitrogen in there or some helium in there, now it can't expand and counteract that. So increasing the pressure this time at a constant volume is going to have no shift. No shift. Why? Well, we're not changing the pressure of A and B anymore. If we think of each A, let's say HA contributed 1 atmosphere and the B contributed 1 atmosphere for a total of 3 atmospheres in there. So the pressure of nitrogen or of A is 2/3, 2/3 or 2 atmospheres over the total. And that's 1 atmosphere. And I pump in another 1 atmosphere worth of nitrogen. Well, what's the pressure of A? Well, it's still 2 atmospheres. We didn't change it. What's the pressure of B? Still 1 atmosphere. We didn't change it. And so when there's a constant volume, the partial pressures don't change. And so since the pressures don't change, then there's always no shift. So whenever they're adding an inert gas, it must state whether it's at constant pressure or constant volume. The only time you will not see it is if you have the same number of moles of gas on both sides. Because then there is no more moles or less moles. It's the same moles. And so it would have no effect. For reactions in solution, it's going to have an identical effect by changing the total volume. Adding water dilutes the concentration. We already talked about this. And very similar to what we just talked about there with adding an inert gas. All right, so the last change we need to deal with is what happens if we change the temperature? All right, so we can understand this by looking at the enthalpy change for a reaction. So exothermic reaction, reactants yields products. Heat is over here. You can consider it as a product. Energy is being released when it's exothermic. And so the delta H when it's exothermic is negative. So heat is a product. So if you raise the temperature by inputting energy in the form of heat, so you heat this thing up, then the reaction will counteract this by shifting away from the heat. Now, if you say that on the AP test, you're going to get it wrong. There aren't a lot of things that I say you got to memorize, and this is one. This is one. Now, we can predict which way it shifts pretty easily. We know that it shifts left. Why? Well, it's trying to get away from the heat when you're increasing the temperature. If you were decreasing the temperature on this, it would shift to the right because it would go towards the heat then. If it's endothermic, it's a positive delta H. And again, same thing. If you increase the temperature, it shift right away from the heat. If you decrease the temperature, it's going to shift left towards the heat. But if you say it again, Matt, on the test, you get it wrong. So here's a phrase you must memorize. I hate to say that. I don't say that often. When you change the temperature, increasing the temperature favors the endothermic reaction. Now, when you're doing equilibrium like this, I'll just do one down here. I'll do my 2A yields B again. Equilibrium with B. Let's say this thing is exothermic. So energy or heat energy, you could say energy, or you could say heat. You could also say the delta H is negative. All right, so going from left to right, this thing releases energy and it's exothermic. But if I look at this going from right to left, it's absorbing heat and it's endothermic in that direction. So each equilibrium has an endothermic and an exothermic direction, depending on where the heat is. When we say something's exothermic, though, we're talking about it going left to right direction. So this thing is exothermic overall because we're looking at it going from left to right when we state that. But there is an endothermic direction. All right, so this phrase right here takes care of what I just said. So the increase in temperature, go back to this one. So heat is on the reactor or product side. Increase in the temperature makes this thing shift left. Why? Well, it favors the endothermic reaction. So we're absorbing heat going in that direction. We're absorbing heat going from left to right. If we look at the other one where heat is on the reactant or the product reactant side, now it's endothermic, increase in the temperature favors the endothermic reaction. Increase in the temperature favors the endothermic reaction. All right, so let's just try some of these and see how it goes. So what are we really trying to do? We're trying to figure out whether it shifts left or right. Now, one last thing is, remember, K is only changed by changes in temperature. So we actually get a new K value when we change temperature. So if we shift to the right, that means we get more products, less reactants, and so K goes up. If it shifts this way, now you get more reactants. So more reactants, less products, and so K decreases. So we can actually change K and we can predict it with changes in temperature. I'm going to go down this side. You're going to try the ones on the right. So let's do this. So what is the effect of adding additional CO? So it's a gas. If we add more of that, it shifts to the left. It shifts away from an increase. What is the effect of adding CO3? Well, that's a solid, and so there'd be no change if you add CaO. Think about that reaction we're talking about. This would be a beaker. Down here, we have some CaCO3. We also have CO, both of which are solids. So we also have some CO. And then up here, we have CO2. It's at equilibrium. Its concentration is unchanging. So if I add more solid down here, we're not going to get more gas because it's already, again, at equilibrium. So you try the one on the right. Again, I'll come back to those. Consider the following reaction at equilibrium. What is the effect of decreasing the volume of the reaction mixture? So notice we have a solid and a solid again. The only one that's going to be affected by that is the pressure. And so if we decrease the volume, Decreasing the volume effectively increases the pressure, and so you want to go to the side with less moles of gas, so it's going to shift left. Increasing the volume. Increasing the volume decreases the pressure, so it goes to the side with more moles of gas. And then adding an inert gas at constant volume. Well, if we're at constant volume, whenever we're at a constant volume, there's no change, so no change. If this was an inert gas at a constant pressure, that would be different. It would effectively, remember, decrease the concentration of the gases, and so it would shift to the right. The effective temperature. So what is the effective increase in the temperature? This says it's endothermic. That means the heat is on the reactant side, or you could say that the delta H is positive. Increase in the temperature is going to shift left, favors the endothermic reaction. Decrease in the temperature goes to the right. Predict whether we go left, right, or remain unchanged. So if we add NO, that's going to shift left. If we add BrNO, that's going to shift right. And if Br2 is removed, that's going to decrease Br2 and it's going to shift to the right. All right, so hit pause and try these. Here goes. All right, so effective adding additional Br to the right. Effective adding Br to the left. Effective decreasing the volume. So decreasing the volume increases the pressure. We want to go to the side with less moles. There's 3 on the left, only 2 on the right. And if we increase the volume, that decreases the pressure. We want to go to the side with more moles. Temperature, what side? So now it says it's exothermic. So heat goes over here. The delta H would be negative. Increase in the temperature, left, favors the endothermic. Decrease in the temperature favors the exothermic, opposite. All right, carbon is added. Well, it's a solid, so there's no shift. H2O is condensed and removed, so the concentration of H2O is going down. CO is added. H2 is removed. All right, so try these as well, and I'll give you the answers. All right, so each reaction is allowed to come to equilibrium, and then the volume is changed as indicated. All right, so first one, the volume is decreased. So volume is decreased, pressure is increased. We want to go to the side with less moles, but they're the same on both sides. There's 2 on the left and 2 on the right, so no shift. Volume's increased on the next one. We want to go to the side, so volume is increased, pressure is decreased. We want to go to the side with more moles. And volume is increased, pressure is decreased. We want to go to the side with more moles. There's only gas on the right. Predict the shift increasing and decreasing the temperature, and how does it affect K? All right, so we only have gases, gas, gas. We have 12 moles over here, 6 moles over here. All right, but this says it's exothermic, so heat goes here. The delta H is negative when it's exothermic. So if we increased the temperature, it's going to shift that way, left, which means we have more reactants than products, which means K goes down. If we decrease the temperature, then it's going to shift to the right towards the heat, towards the, favors the exothermic reaction then. Now we have more products, and so the K goes up. If the reaction is at equilibrium, predict whether each disturbance will result in the formation of additional hydrogen, less hydrogen, or have no effect on the hydrogen. So if this thing shifts to the right, the hydrogen gas goes up. If it shifts to the left, that means the pressure in the hydrogen gas is going to go down. So we're looking for whether this is going to essentially shift left or right. Adding more carbon, no shift. It's a solid. Adding more water, it's going to shift to the right. Hydrogen goes up. Raising the temperature, it's endothermic. So the heat is over here. So raising the temperature shifts right. Hydrogen goes up. Is increasing the volume. That means the pressure goes down. We're looking for the side of more moles of gas. So that's right. Again, goes up. Now a catalyst will get us to equilibrium faster. And if we're already at equilibrium, like this one is, then it has no effect. Adding an inert gas to the reaction mixture now, is it at a constant volume or a constant pressure? That would be the question here. So what did I write down? I remember doing this. Oh, I just said both because it doesn't say. All right, so if this is at a constant, let's say it's at constant pressure. All right, so constant pressure, when you add a gas, remember that effectively increases the volume, which decreases the pressure of each gas. So the fact that it decreases means we want to go to the side with more moles, which would be to the right, and hydrogen would increase. But if this thing is at a constant volume, we already know there's always no shift. So if there's no change in volume, there's no shift. I'll just give you these. Again, pause if you want to try them. That goes to the right. This is no shift. That goes to the right. Number 4 to the right. 5, 6, oops, 6, and no shift. All right, now these next few pages, you can just read. So this was the Haber process is specifically mentioned as an equilibrium reaction in the AP curriculum. I describe here what the Haber process is, who Haber was. Fritz Haber, he was a scientist, worked in Germany. He's actually part of the Nazis. And it describes coupling reactions here too in physiology, and then in blood, some more equilibrium, pH, carbon monoxide, and then some of these to try again. So again, hit pause, try these if you'd like before I show you. And here it goes. So again, I'm just going to put the answers, although these are a little unique in that they're asking whether each one is going up or down, and then K. Remember, K is only affected by changes in temperature. If you add more hydrogen, this thing shifts to the right. What happens to nitrogen? Well, it goes down, and then that goes up, but again, no change in K. Adding NH3, it shifts to the left, which means NH2 is going up, hydrogen's going up, and then once again, K is only changed by changes in temperature. Remove N2. So H2 goes up, NH3 goes down. Remove H2, same thing. NH3 or N2 goes up and NH3 goes down. Shift to the right. Both of these are going down. Once again, no effect on K. Changes in temperature, though, do affect K. This thing is negative, which means heat is over here on the product side. So if you increase the temperature, it's going to go left, which means hydrogen and nitrogen go up and ammonia goes down. All right, now shifting left means we have more reactants, so K goes down. If we decrease the temperature, it's going to go to the right, which means this goes down, that goes down, that goes up. Now we have more products, so K goes up. Increasing pressure, side with less moles. Decreased pressure, side with more moles. 4 ways to increase the yield. You can figure that one out, but you're looking for 4 ways to make this thing shift to the right. The Haber process talks about this. Notice there's moles on both sides. So if we want it to shift to the side with less moles, we want the pressure to go up. So we could decrease the volume of the container. We can add NO2. We can remove N2O4. It's exothermic. So we could decrease the temperature. There's 4 ways. Now this one's endothermic. So we have heat over here this time. If we add H2, it's going to shift to the right. If we add I2, same thing, right. This goes down, that goes up, and K unaffected. Add HI. Remove H2, remove I2, remove HI. We're increasing the temperature. So it shifts to the right, which means K goes up. More products. Left. K goes down, more reactants. Increasing the pressure, the side with less moles, but you can see we have 2 moles on both sides. So neither of these are going to have any effect. No shift. And the last one, no shift, it's a solid. Adding NaCl is effectively adding Na, so it shifts that way, adding OH. Removing OH. This is a big one when you add an acid. So that would be an acid to something that has a hydroxide. We're going to revisit that. Negative, increasing the temperature then shifts, and then K goes down. Decreasing the temperature, though, it shifts right, and K goes up. Increasing the pressure, and there's no gases in these, so this is no effect. All right, so that's Le Chatelier's principle. Keep working, and sign up for a Zoom if you need me, and we're still right on schedule.